Good morning. It's 9:41. Let's go ahead and get started. Welcome to Data 100, lecture number 7. Today we're going to be talking about exploratory data analysis as well as working with text. Before I get started, I just kind of wanted to try out my knowledge of you guys' names. So I'll try to do my best. So if you've ever interacted with me and have ever gotten your name, I'll try to remember them now. So I think I see Sophie, is that right? I see Eva in the back. Hi, Eva. Who else do I have here? Matt, hello. Jesse, is that right? Danny. Ruby, right there in the middle. Peyton, is that right? Behind Ruby. I got Ishan, my TA, in the back. Ariana, is that right here in the front? Is that? Huh? Eliana? Okay, I was kind of close. Okay, so if I did not remember your name, I do apologize, but I really try to remember people's names. If you've talked to me and if I've introduced myself to you and you've talked to me about it, I will really try. I'll do my best. And if you want me to remember your name, then you can just come ask me a question after class or during office hours or during class if you like. Okay. Some announcements. We have homework 2 coming out today, homework 3 coming out Friday. I have some students who are requesting deadline extensions, and basically I've given my TAs the power to grant extensions, so you should talk to them instead of to me about extensions. So we only grant extensions in extreme cases, or if the Disabled Students Program gives you some special accommodations for it. But for example, if you're going through something really serious, our priority here in this class is not to enforce all the deadlines to the letter, but is to make sure that you can have the time you need to really learn the material. And oftentimes, having a really tight deadline causes you a lot of stress and hinders your ability to learn, which is not good for us because our goal is for you to learn as much as possible, as efficiently as possible in this class. So that's kind of my philosophy on deadline extensions. But I really do encourage you to not request them because it'll just create a lot of load for us unless you have some extreme circumstance. Okay, congrats on finishing project 1. I think you guys should give yourself a round of applause for that. It's a long project, it's a long assignment, but I hope it was useful and I hope it was relevant. I know a lot of the restaurants in that data set I've actually been to personally. If you saw Tartine or Bayreuth, those are some of my favorite places to go in San Francisco. If you haven't been to those places, I really encourage you to check them out. And we're going to be using some of the data in Project 1 as part of our discussion around exploratory data analysis today. Okay, let's talk about EDA. So if you remember this slide from the very first lecture, we talked about the data science lifecycle. And the data science lifecycle is roughly divided up into these 4 steps. We have here designing or formulating a question or a problem, acquiring and cleaning the data, and then doing exploratory data analysis to understand the data. And then finally, we draw conclusions, inferences, or predictions from this data analysis process. Okay, and today we're going to be talking about the 3rd step in this process. We've gone through a little bit about question formulation. We've gone through data cleaning and data acquisition and how to work with different data formats. And today we're going to be talking about exploring your data set and coming to understand it. Okay. Basically what we do in data science is we enter this iterative process where we visualize and transform the data. We try to see patterns, issues. We try to see these things to inform subsequent analysis and discover potential hypotheses. You do have to be careful with designing hypotheses based on exploratory data analysis. If you've heard the term garden of forking paths, it refers to all the possible hypotheses that you can run on a particular data set. And if you use exploratory data analysis to select an hypothesis to run an hypothesis test, it can negatively influence your results. So basically if you want to explore the data and find patterns, the rule of thumb here is that if you want to really do some hardcore inference on a particular data set, what you should do is you should collect a data set for exploring and then a completely separate or ideally independently collected data set for inference. So you should perform your analysis in 2 steps. 1 step to explore the data to find patterns to test out, and then test out your patterns on a data set that you haven't seen before. That's to avoid the issue where you kind of snoop around in your data for patterns and then confirm those patterns using a hypothesis test. Okay, we're going to be talking about that a little more when we talk about p-hacking, but I want to give you a preview and a heads up today during our lecture on EDA. Okay, one important aspect of EDA is to have an open-ended attitude. And in particular, what you're looking for is patterns that you expect to see, as well as patterns that you did not expect to see. For example, if you're looking at income data, you might expect that income data is heavy-tailed to the right, to larger incomes, because there are a few people who have much higher incomes than the rest of us. But if your data come to you and you plot that histogram of incomes and it looks different than what you expect, then you might question whether your data are a random sample from a population of interest. Okay. All right. In particular, in this class, we divide up EDA into these roughly these 5 components, which is data types, granularity, scope, temporality, and faithfulness. Let's go through each one of them. All right. So for data types, there are many ways of breaking up types of data. In this class, we're only going to look at 3 rough categories. We're going to be looking at nominal or categorical data, which are categories without a natural ordering, such as, let's see here, such as political party affiliation, for example, or classes at Berkeley. We can also have ordinal data, which are categories with a natural ordering, such as t-shirt sizes or education level. And we also have numerical data or numeric data, which, that should be amounts or quantities. I apologize. Fix that now. Numeric data represent amounts or quantities. These are continuous numbers. So for example, heights or the temperature on a particular day, or the wind speed, for example, are all continuous quantities. Okay, one important distinction between numerical data and the rest of the data types that we have in this class is that the differences, the magnitude of the differences between data points is significant, has meaning, in other words. For example, if you go from a height of 4 feet to a height of 5 feet, that's twice as big of a difference as if you go from 5 feet to 5.5 feet. Whereas for ordinal data, going from a small t-shirt to a medium t-shirt and then from a medium t-shirt to a large t-shirt is not necessarily the same magnitude of difference. One notable example of this is Likert scale questions, which are commonly used on psychology surveys. So you may have seen you rate something on a 5-point scale of strongly disagree to neutral, and then agree and then strongly agree. And oftentimes what people will do is treat those responses as numeric values. So for example, they'll take the average of those numbers, they'll number them from 1 to 5, and then take the average of those numbers. And that average doesn't really have too much meaning, because the difference between strongly disagree and disagree for a particular person may be much wider or much smaller than the difference between disagree and feeling neutral about a particular statement. Okay, so you do have to be careful with numeric data. Numeric data is defining trait is that, for example, the average of values has meaning, subtracting values has meaning. You can do numeric operations on numeric data. Okay, we call these statistical data types. Since we're going to be using these data types most commonly in this class, from now on, I'll just refer to these types as data types without putting the statistical in front. But the reason why we have this word in front is because these are distinct from what we call computational data types. Okay? Computational data types are the types that the computer assigns to your data, not necessarily the types that you want to use in your data analysis. For example, when you read in a CSV in Pandas, Pandas will automatically assign every column a computational data type. So for example, if you read in a CSV and the column contains numbers, then Pandas will automatically infer that that column should contain numbers. So it'll mark that with say an int type or a float type. But just because Pandas marks a column with a particular data type doesn't mean that you should treat the data as that data type. For example, in a lot of data, we see that sex is coded as 0 for male and 1 for female and 2 for missing, for example. I think this is true of census data. And in census data, they also have another category like 999 for like the sum of all ages. And so when you read this data into pandas, pandas will treat that column as numeric or integers because you have 0, 1, and 2 in your data column. But you should not treat that column as numeric data because it doesn't make any sense to subtract 1 minus 0. You can't do numeric operations on this particular column because the data are really representative of nominal data or categorical data, not numeric data, despite how they're represented in the data set itself. Okay, so I have here a condensed data set from project 1. If I take this data frame and in pandas or in Python write df.dtypes, I get this output, which says that the ID column has the data type, the computational data type int64, which essentially you can read as an integer. Okay, the lat column has the data type float, and the phone column has data type object. And for pandas, usually when it marks a column as object, it's referring to strings. Okay, so my question to you is, what do you think are the statistical data types for each of these columns? So I'm going to have you guys talk with your neighbors for like 1 minute. I did want to start with one caveat or one personal note about talking with your neighbor. I remember when I was a student, I hated participating in class because I was like, I just want to learn on my own, do my thing, and get out of here. And I think, let's see, there was one particular class where I decided to myself, like, you know what, I'm gonna try out this experiment where I go to lecture, get as much out of lecture and discussion as possible, and see if I can reduce the amount of time I spend studying or struggling on my own by just going to class and trying to make use of class time. And it turned out to work really well. And so I was convinced at that moment, and via a bunch of research studies that people do on education and learning, that essentially it turns out that even though talking in class is not the funnest thing for some people, especially for introverts like myself, it turns out that when you talk to your neighbor, even if you don't figure out the answer, you'll remember the information that comes after much better. And so it's one of my personal goals for this class is to just make the class as efficient as possible in terms of learning. One way to make the class more efficient in terms of learning is to reduce the amount of time you need to spend to learn the same amount of material. And participating in class is one way for you to increase your learning in a shorter time scale because you're sitting here in class anyway, so you might as well make use of the time to participate, thereby reducing the time you need to spend studying. All right, that being said, go ahead and talk with your neighbor. I won't look down if you don't talk, but if you do talk, you may benefit. So what do you think are the statistical data types for this data frame? Go ahead. All right. What do you guys think is the statistical data type for the ID column? So it's coded as an integer in pandas, but would you treat it as an integer or would you treat it as numeric data? Can I get a volunteer? What did you guys talk about? What is a data type for the ID column? Yeah, Danny?
Maybe the latitude column
Yeah. So Danny says we should treat the latitude column as numeric data. I think that's pretty true. I think it's pretty true. I would say the ID column probably should not be treated as numeric data because you can't, the difference between business IDs is not particularly meaningful. It may be the case that later IDs were entered into a database at later points in time, but that's not necessarily true of all data sets with an ID column, so it's not a good assumption to make unless your data description says that the ID columns were entered in from like oldest to newest. Okay, the phone column is stored as a string in the pandas data frame, and I think that we should probably treat phones as either categorical data or maybe ordinal data. But most likely my leaning here would be for nominal data because the ordering of phone numbers doesn't have too much meaning in and of itself. Okay, talking about granularity. Granularity asks a question like, what does each record represent? What you want to make sure when you acquire a data set is you want to check whether every record captures granularity at the same level. Census data is particularly notable, for example, for including rows that have the sum of certain numbers. So for example, there are some columns that have the sum of male and female counts or the sum of particular age ranges. So you do have to be careful that every record has the same granularity. If the data are coarse, such as if the data are taking the average of weekly incomes, for example, like the data set we looked at yesterday, you really want to know how these aggregations were performed. Sometimes they will sample, sometimes they'll take the mean, sometimes they'll take the median, and knowing how the aggregation is performed is important. Okay. You can also aggregate yourself to change the granularity of a data set. For example, you can group businesses together, you can group individuals together to form categories, you can group times together. So for example, you can group by the day of the week, or you can group by the month of the year to to make your data more coarse, which decreases the granularity of your data. And so to adjust the granularity of a data set, you use group by operations and pivot operations, but mostly group by operations. Okay, so I have here a data set from the project, and we asked you the question on the homework itself: what does each record represent? What is the primary key? What would you find by grouping by the following columns individually? Okay, so this was a question. I copied and pasted this out of the project, which means you should already have an answer. Maybe it's a good time for you to check whether you agree on your answer with your neighbor. So talk about it for a minute, and we'll come back. All right, let's bring it back together. So I'm going to ask one more volunteer to share, or if you feel brave enough to share your answers from your project. What does each represent? What's the primary key? What would you find by grouping the columns? What did you think? Yeah, name? Wait, what's your name, sorry? Frederick. Hi, Frederick.
I think each record represents like inspection or company or business. Primary key is like business ID.
Okay.
And if we group by each ID, I think it would be the same because each inspection is unique. If we group by name, there might be like repetitions because
Yeah. So Frederick says that this data set has each record represents one inspection of a restaurant. Is that right?
Yeah.
And then the primary key is a business ID. And if you group by the business ID column, nothing changes. But if you group by name and address, you get something that's more coarse than what we had before. And I would say for this particular question on the project, the data set that I have here is actually just the restaurants themselves. So I think your answer would be right if we asked a question about the inspections data frame. But this right here is the business data frame or the bus data frame on project 1. And so in this case, each record represents a restaurant, all right? Because we noticed in the project that some restaurants were repeated. So for example, Starbucks Coffee appears many times in this data set, but Starbucks Coffee itself is a single business. So the same business appears multiple times, one for every restaurant that it owns. I would not say that each record in this data set represents a location, because some addresses can appear multiple times and some restaurants don't have an address. So I would say that the granularity of this data set is the restaurant and not the business or location. Okay, the primary key is indeed the business ID because that column is unique. It uniquely identifies every row of my data. If you group by the business ID, as Frederick says, you would get the same data set. You would pretty much get the same data set more or less no matter what you do to it because the business ID column is unique. If you group by the name column, you would do operations on the business level, right? Because grouping by the same name restaurant is like every group of the same restaurant name roughly corresponds to one business. And grouping by the address would let you do operations on restaurants at the same location. Okay. Let's talk about scope. So the question of scope is a question of what my data describe. We often want to know whether the data cover my area of interest. For example, if I'm studying crime in California, but I only have Berkeley and Seattle crime data, then what I need to do is slice away the Seattle crime data, but that will only leave me with Berkeley data. If I want to make a conclusion about California, I would be pretty hard pressed to do so unless I make some very strong assumptions about the representativeness of Berkeley's crime data compared to California's crime data. So in general, the takeaway here is that you can only make statistical inferences about probability samples from the population of interest, which means that if you're trying to make a conclusion about California as a state, you need a probability sample from California. You can't just make do with a probability sample from Berkeley unless you make some strong assumptions about the representativeness of Berkeley. Okay? All right. Oftentimes you'll just make the assumption anyway. Like in real life, sometimes you won't have the chance to go out and collect probability samples. But if you do make assumptions about what your data represent, then you should really be clear and record down those assumptions somewhere so you can investigate whether those assumptions hold or not in the future. Okay. Sometimes you have more data than you need. So sometimes your data go beyond your area of interest. For example, if you're actually interested in studying just crimes in Berkeley, but you have data across California, then that's an easier problem to solve because you can slice away the data from California and keep the data in Berkeley. The one caveat here is that if you have a sample over a large scope, then that may result in a pretty small sample once you slice away the population, once you slice into the population of interest. So for example, if I took a random sample of size 100 from across California, I may only get a few data points within Berkeley, and that'll make my conclusions not so great. Okay, so that's the one caveat when it comes to scope. Obviously, in the ideal case, your data would closely match the population of interest, but in real life, you have to determine how much, what your data cover, and then you have to determine whether that coverage is sufficient for the analysis you want to do. Okay. So the business data set in project 1, was it a sample or a census? And what time frame did it cover? I'm running low on time here, so I won't make you discuss. But the business's data set, how you would find this out is we didn't describe it in the project itself, But if you go online to the San Francisco dataset website, you would see that the business's inspections dataset is a census from all the inspections from 2016 and onward. Okay, so it is a census, but only for a specific time frame. If I'm interested in the inspections in 2017, then I would have a census for that particular time period. If I'm interested in the restaurant scores across the past decade, then I would not have a census. I would have a sample, an administrative sample. Okay. Temporality. Timestamps are of particular importance to us as data scientists, but they also pose a lot of difficulties. So for columns, we want to know what the meaning of the date time field is. Unfortunately, every database will encode this field differently. Some of them will record a timestamp when the event happened, or they'll encode a timestamp when the data were entered into the system. And sometimes some databases will just record a timestamp when you're copying data from one database to another, and that sort of timestamp is not particularly useful to us at all for making inferences about the real world. Okay. Time and time formatting also depend on location. We talked about this briefly in data cleaning, but basically time zones just have, working with dates and times is just a pain in the butt because you have time zones, you have daylight savings time, which is just an absolute disaster because some places in the US change daylight savings at different points in time. I believe there's a city that follows daylight savings, but then there's a very small neighborhood within that city that decided not to follow daylight savings. And so if you're working with daylight savings, if you're working with timestamps and time zones, you really want to be careful about working with time zones and daylight savings. You also want to be aware of regional formatting. So timestamps in the US may be formatted differently than timestamps from other parts of the world. Something you have to be aware of. Okay, you do also want to be aware of weird values. So in particular, for some common computer systems, the value 0 in the time column will be encoded as January 1st, 1970, which is called the Unix epoch. So if you look through your data and you notice a lot of timestamps on January 1st, 1970, that should raise some yellow flags for you that you want to investigate whether those are missing values or whether those were actually supposed to be there. Okay. Talk about faithfulness. Faithfulness refers to kind of this broader degree, this broader measure of how much I should trust the data. Essentially, if your data are really messed up, then you shouldn't trust it. And the process of determining faithfulness is a process of determining how messed up your data are. Okay, so we're looking for unrealistic or incorrect values, dates in the future, for events in the past, locations that don't exist, for example, like off the grid in project 1, negative counts, misspellings. There's a lot of ways the data can go wrong. There are other ways, there are more subtle ways the data can go wrong. For example, if two columns should be consistent, but they are not. So like if the age of a person and the birthday of a person doesn't match, then that should alert you that something is up. If you know data were entered by hand, you should be alert. If you know the data entry format had default values, then you should be aware of what those default values are. And you should look for deliberate data falsification, especially when it comes to sensitive data like health records, or perhaps like income level. You do want to be, or like political party affiliation or voting patterns. All that sort of stuff is very susceptible to people being shy or not wanting to share their data accurately, and that results in some bad data. So you should be careful and aware of these things. You can't just assume that a data that comes to you in a CSV file is data that you should use for inference. Okay. I want to conclude this section on EDA by noting that EDA and data cleaning are this iterative cycle. Okay, so we have to introduce them separately in this class just to make them fit within the lecture format. But in reality, what you'll do is you will start cleaning your data, you'll explore the data, and you'll notice anomalies. That'll put you back in a data cleaning step. And then after you clean up your data some more, you'll go back to EDA and try to understand your data. And that whole cycle is just a long, it can be quite long depending on how your data come to you. But basically the point of both these two processes is to prepare your data so you know what are the conclusions I can draw and what are the things I should watch out for. To give an example, when we were preparing project 1, we took the data set from San Francisco, and we started looking through the data to see whether we can turn it into a homework assignment. There are a lot of candidate data sets that we look through in order to determine which one to give you for an assignment. And you have to hit this sweet spot, or at least for us, we're looking for this sweet spot of like, it can't be too simple because it's not realistic, but it can't be too complicated or too messy because even though that's realistic, it's just tedious and quite a pain to work with, especially for learning purposes. And so in this case, we like looked through a bunch of data sets, found out that this business's data set was messy, like kind of hit that sweet spot of messiness. But when we were looking through that data, we were looking through the zip codes and we were trying to figure out what was in that zip code column. We tried to plot the zip codes on a histogram, like treat it as numeric data just for plotting purposes. So we tried to cast all the zip codes to ints upon a histogram, but we noticed that there are missing values. Okay, so you did the same thing on your project. We were trying to guide you through sort of similar steps as what we went through when we were trying to understand this data set. Okay, so we also ran into this issue where we were like, oh, there's missing values. Okay, let's see if we can drop them for the time being just for plotting purposes and replot. We tried to replot them, and then we were like, crap, there are like weird zip codes in here. Like there's like CA as a zip code. So we like, I cut off most of this error message here, but in reality, like we ran into like this page-long error message that said something like, in the very bottom, invalid literal for int with base 10 CA. That sort of error results from trying to convert a string into a number when the string doesn't contain numeric characters. And so we were like, okay, that's not good. Maybe we should just whitelist a set of zip codes and keep only the zip codes that are in San Francisco. So if you remember writing the code like that involved the isIn method, that's exactly the same sort of code that we wrote when we were looking through this data set. We can filter out the zip codes by only the zip codes that we know are in San Francisco, and that let us finally plot a histogram. But that sort of histogram doesn't look super great, right? So we did this and we were like, all the zip codes are in one clump. And this usually arises because there's some smaller zip codes and some large zip codes, right? So we have here on the x-axis, it's a little hard to see, but it goes from 0 to 1 to the 1 times 10 to the power of 8, right? Which corresponds to very large numbers. And that tips us off that maybe the zip code column, despite filtering, does not have super great values after all. By looking at the zip code values, we see that there are some like 9-digit zip codes, which are totally valid in terms of like using like the postal service, but are not super good when it comes to understanding the data. So we cleaned those up to be 5 digits, and we made you do the same thing on the project. So we cut off the last 4 digits of those zip codes, and then we plotted them. And then we noticed that, okay, that seems pretty reasonable. Most of the zip codes come between 94100 and 94200. And it seems that like even though there are some messy values, enough values were good enough that we could actually give this assignment to you as something that you could work with as a beginning data science student. But of course, it doesn't end there. Now, once we verify the zip codes look relatively reasonable, then we have to go back to the missing zip codes that we dropped at the very beginning and determine whether those are reasonable or not, or whether those should be dropped. And on the project, we noted that the missing zip codes correspond to, I believe, like restaurants that are off the grid or don't have a permanent location. And that's the sort of thing, this is just one small slice of the data cleaning and EDA cycle that we find ourselves in all the time as data scientists. So we try to give you a little taste of it on project 1, but really like this is something that you'll be doing for the rest of your career if you end up doing data science. All right, let's take a break. And I will open up this form. Go ahead and fill out that form now. Yeah.
week I still just give them credit because they still need to show up to all the lectures in the week.
Yeah, I think so.
Yeah.
Yeah, I'll give him credit for tomorrow.
No,
That's good.
I can just answer that on the outside if you want. And I'm trying to run the make assign, but it's the J assign of still doesn't seem to be working. So I emailed Professor Benitez to see if I can figure that out. But I'm still waiting.
Did you get a message on Slack?
Yeah, it's so
Okay.
it's like he said the same thing that you need to update Python. So I did was I tried running, Python 3, JSign and the thing, but it still didn't seem to be working, so I don't know what the exact issue is.
Okay.
And it's weird because I'm the first person running into issues with the JSign file. We had
Yeah.
the make file and the disk, but this is
Yeah, I unfortunately am not too familiar with how that stuff works. If you can try to get a reviewer, I mean, one thing we can do is you can push your change to GitHub, and you can ask another TA to run JSign for you to see if that.
oh, it's already done.
Oh, it's already done.
Like it's already been pushed.
Oh, okay.
Like the edited homework due
Yeah.
version with the JSign tags has
Yeah.
been pushed.
I see. So we could ask someone who has JSign working to just like push it to the public repo, and then you can look through it to see whether everything looks good. If they can push it, then we can essentially publish the homework now and then work on the JSign issues later.
Okay,
That'll
that
give us
sounds
some more
good.
time. Yeah. So
I'll
we can
message
try to do
someone.
that. All right, raise your hands if you're still filling out the attendance form or if you haven't gotten to it yet. All right, closing. Okay, so let's talk about text. We single out text in this class because essentially, like, working with text is working with the ability to work with text gives you the ability to work with a wide variety of human data. A lot of the data online or available in the world today come in the form of text. For example, people write all sorts of things on Twitter and Instagram, which all come in the form of text. People enter in data using their email addresses, which are text data. And so the ability to work with text kind of opens the door for a lot of interesting data analyses. I want to talk to you today about how to work with text in Pandas, as well as a specific tool called regular expressions that we use to parse more sophisticated patterns in text that you wouldn't be able to do with Python or Pandas methods alone. Okay, so one reason why we use, one goal for us when we work with text data is to extract some quantitative values from the text. So for example, like if, for example, in a blog post, you might have the date of the blog post published inside the blog post text itself. You might have the time of the post published in the text itself. Another reason why you want to work with text is because a lot of times, or in many cases, data sets will include a special string for missing values instead of just the value NaN. And in cases like that, what you want to do is identify what string represents missing values and then try to record those as missing as opposed to just another value in the data set. OK. One common use case for working with text is working with log files. So in this case, or a long time ago, web servers online used to record down everything in a log file. So for example, in this particular data set, if you visit the website for stat141 here, the web server would put down in the log file, OK, this is the request that came in, this is the date of the request, the time of the request, and this is what the request was looking for. And so one useful thing to do with data like this is to extract out that date and time in order to maybe make a plot of a time series, in order to inform more data analysis in the future. OK, so let me show you how we can do that. Close this. All right. So I have here a log file. Let me move this down, make that bigger. OK, I can take a look at this log file, and it just has 3 lines of text. So there's one line here. It's just a little hard to see because it's a really long line, but this is one line, and it wraps around here. So this is one line. This is the second line of text. This is the third line of text. And what we want to do with this text is extract out this date and time and turn those into something that we can use either in a data frame or as a date-time value. Okay. One way we can do this is to open that text file and read in all the lines. Okay, so I have here the lines as a Python list. I can assign this to lines. I can take the first line of that text. And here's the first line. Lines. There we go. So here's the first line of text. And now I'm going to try to take a look and extract out these values here. So the way to do this in Python is to use a split method. So I can take first.split. So I'll show you a bad way to get out the timestamp. I'll show you a better way to get out the timestamp, and then I'll show you a really good way to get out the timestamp. But let's start with the bad way. So the bad way is to split. Split on this bracket here. Okay, I'm going to split on that bracket. I'm going to take out the second element. I'm going to take out this portion of the string. Split on the right bracket. Let's see here. Or split on the space, sorry. So I have here this containing the timestamp. I'm going to ignore the time zone, even though in practice you would definitely not want to ignore the time zone. But just for today, I'm going to ignore the time zone. Take the 0th element of that list to get out just this portion of the string here. All right, I'm going to say time stir. OK. Then I can split this guy on the slash. Right, and so I can call this day, month, and rest. And then take the rest and split the rest on the colon character. And then assign this to year, hour, minutes, seconds. So you can kind of see how tedious this is getting. And then I can put all these together. I can put the year, month, day, hour, minute, and second. And now I've extracted out all the fields of this particular timestamp. But it took me a lot of work. And it's quite brittle because, for example, if one particular line in the log file comes around and it doesn't have a space in the exact location that I want, then all hell breaks loose and I get some bogus data. Okay, so this is the way to do it with Python methods. But for this particular example, it's not the greatest. And the reason why it's not the greatest is because I'm not trying to, my goal here is not to split up the string into really small values. My real goal is to find the pattern in the string and extract out the part of the string that matches a pattern. Okay? And so we'll use regular expressions to match patterns in strings. But before we get there, I do want to show you how to work with strings in Pandas. So if I have a series, if I had a bit of code, if I had a function to perform this operation for me, then what I could do is write a for loop over the lines in my log file. And for every line in my log file, I could just perform that snippet of code right there and extract out all the fields of the timestamp. But usually in Pandas, if you find yourself writing a for loop, you're doing something wrong. Okay, so usually what you want to do is look for the built-in pandas method that will do the looping for you. And in this case, what I can do is put the lines in a series. And when I have a series of strings, I can use the stir attribute. And the stir attribute lets me call string functions as though they're individual strings. Okay, so I can do string.split just as if I can pretend like everything that comes before the dot split is one string, and pandas will automatically write the for loop for me and split across every one of these strings individually. So if I write stir.split, what will happen is the first line will get split right here, the second line will get split right here, and the third line will get split right here. Let's see what happens. Okay, so now this series contains a list, or this series contains lists of strings. And what I can do is pass in the expand equals true argument to make that a data frame. So I have here this part as a data frame. I can grab out that first column here. Let's see, is that right? Yeah, grab out that first column here, and I can repeat this process, for every part of that string that I want to do. So I'm just trying to show you here that if you can do an operation on a single string, you can do the operation on a series of strings by using the pandas stir attribute. I won't go through all of this here. Instead, I'll just take this code here and paste it in because it's quite tedious. And I think my point is clear. OK. All right. So let me show you the better way of doing this, which is to use regular expressions. To use regular expressions, we import the built-in RE module, and we write a pattern. In Python, we write this R character in front of the string to say it's a raw string. And essentially, the reason why we do that is because backslashes in strings have to be escaped. So if you write \n as a string here, this pattern variable actually contains only one character. It contains what's called the new line special character. And that's because the backslash has a special meaning. But most of the time when we're working with regular expressions, we want to use this backslash character, but we want it to be part of the pattern itself and not like as some weird escaped thing. Basically, the takeaway here is that most of the time you should put the R in front of a string so that you get a non-escaped backslash. So you see here that I get, when a string outputs in Python, it has to escape the backslash. The takeaway here is, if that was all confusing, just remember, if you're writing a regular expression and things are going weird, and you forgot the R, you should put in the R and see if it works. Okay. So that being said, I can write a pattern that looks like this. I can say grab some digits, followed by slash, followed by some alphanumeric characters, followed by slash, followed by some more digits, followed by some more digits, followed by colon. Okay, so I can do this a couple times. Okay, and let's see here. I have one slash. I have to make sure these colons match up. Take this pattern here. And what I can do, and I'm going to explain what this pattern is in a second, but basically the takeaway is if I write a regular expression, it matches a pattern within the string, and then I can use the RE module to grab out, to match the string against the pattern. So I put in re.search. And you can see here that when I do re.search, it says I found a match within the string that you gave me. This is the match. And if I want to get out the individual components of that string, I can do .groups, like so. And now I have the same result as I had up here in much fewer lines of code, like so. So I've done the same thing as I did above, but it's it's more succinct and ideally, hopefully less confusing. And the reason why it's so is because I used a regular expression to match a pattern instead of just using a bunch of split operations. Okay, let's talk about regular expressions. So this pattern here is quite confusing and it's quite advanced. Writing a pattern like that following is kind of the goal of this class at the end of this lecture. But for now, we can start simple. A regular expression can be as simple as, I'm pasting this code here, and let me show you the value of this first string. The input to a regular expression or the pattern of a regular expression can be as simple as just the copied and pasted text of a string. So if I do that, and then I do re.search, like so. It didn't work. Maybe it's group. There we go. Okay. And so, let's see. What I've done here is I've written a regular expression that says match the character 2, and then the character 6, and the character slash, and then J, and then A, and then N, and so on and so forth. So every character here is taken literally. And if you don't use any special regular expression like characters or like meta characters, then by default, every character will be taken literally. So this regular expression will match this part of my string, but it won't match the other strings in my data set. So I had here a set of lines. This particular pattern here will match the first line, but it will not match the other two lines because these other two lines don't have the literal characters 2, 6, and then Jan, and then 2014. Okay? So what I want to do is I want to say, okay, well, don't match the exact characters 2 and then 6. Instead, you can put a wildcard character. So I can say, instead of matching 2 and 6, match any 2 characters. So the period in the regular expression says match any character. The JAN I can replace with 3 dots. I can replace the 2014 with 4 dots. I can replace the 10 here with 2 dots, the 47 with 2 dots, 50 with 2 dots. Okay, so the dots are wildcard characters, and that means that they'll match any character as long as I can find this pattern within my bigger string. Okay, so this says match any 2 characters plus a slash, any 3 characters and another slash, any 4 characters and then a colon, okay, so on and so forth. And when I run this code, I'll get back the same result as I did before, just that this time I don't need this string to contain the numbers 2014. It'll also match 2015, 2016, so on and so forth. Okay, are there any questions about what I did here? Yeah, Emily?
So that will work for the first entry, the January 26th entry, but what about the February 2nd entry since there's only 1 digit?
Yeah, so that's a great catch, actually. Emily points out that I have here 2 characters and then a slash, but that will not match the second line of code here, or the second line of the log here, because the number in front of the slash here is only a single digit. So what will actually happen is, let me pull out a second string. And if I take that second string and match it, I'm going to also get this bracket in the front because it's going to match any 2 characters and then a slash, which means it's going to pull out this bracket, which is not good. It's not exactly what I want to do. Okay. And so what I can do here is I can say, well, I don't want any character here. I want actually a digit. So if I put in \d, that says that I will only match numbers. Okay, so \d means only matches the characters 0 through 9. And so if I do this on my first string, I will still match, but on my second string, I will not match. It'll give me an error because it doesn't have a match there. Okay. Suppose that I did want to match this number anyway. So I should be able to pull out this part of the string, even though the number of digits here differs. What I can do with the regular expression is I can say, instead of matching 2 digits, I can say match 1 or more digits. So match at least 1 digit, but you can also match any number of digits as long as there's at least 1. To do that, instead of writing 2 \ds, so each \d refers to a single number, I can do a single \d, but use the plus symbol. Okay, so if let me wrap this in parentheses here to make it a little more clear what I'm doing. So this \d plus says match 1 or more digits. And if I do so, I will still match the first string, and I will also match the second string. Okay. Another thing to know about regular expressions is that if I want to pull out subcomponents of a pattern, I will wrap that part of the regular expression in parentheses. You saw me do that in my first example here, where I had like \d plus, and I wrapped that in parentheses. And every time you wrap a portion of a regular expression in parentheses, you'll get what's called regular expression groups, and you can pull out the groups by using the groups attribute, or the groups function of a regular expression search, okay? So if I do .groups, I will get out just the first part of the string here because I haven't asked the regular expression to capture more groups. If I want to capture the rest of the string, the other groups that of interest to me, I can write parentheses around the other parts. Parentheses here, so on and so forth. Okay, so now when I ask for the groups, I will get back more groups because I've told the regular expression to match more subgroups within the larger string. Okay, I can do the same thing for the first string. So you see here now that I have a flexible pattern, right? I have a pattern that I can use to match multiple strings by using the wildcard characters of a regular expression. If I want to be more specific about what I'm matching here, I can replace these dots with other special types of metacodes. So this \d is a more specific wildcard character. Instead of matching any character, it only matches digits. There are also other special characters. For example, \w says match any word character, which is any, I believe, like letter from capital A to capital Z, as well as lowercase a to lowercase z. So if I write W+, I will also match this January, but I will not match strings that have 3 numbers here instead of the word Jan. Okay, so usually what you can do, let me repeat this entire process just to give you, just so you can see the process that I use to build a regular expression. So when I'm building a regular expression, oftentimes the easiest way to do so, and the least confusing way to do so, is to copy and paste in the original string. You saw me do that at the very beginning because most characters are just matched literally. So if there are special characters, like for example, if I wanted to match this bracket here, I have to escape it in a regular expression because that bracket has a special meaning. But most characters are just matched as is. And so because of that, I copy and pasted this part of the string and put it into my regular expression. And I was able to get a match on the first string, but not the other lines in my log file. And then what I do is I start replacing the specific characters in my regular expression with more general characters, with wildcard characters, so I can match other strings that I'm interested in. So you saw me do 26 Jan 2014, and I replaced the first 2 numbers with 2 dots. I replaced this part of the string with 3 dots. I replaced this with 4 dots. Okay, so I had here the dots. And then usually the last step is to use more specific wildcard characters than the dots. But by building up the regular expression in kind of this iterative, incremental way, you can hopefully avoid bugs and get a better sense of what's going on in your regular expression. Okay, so if I were to write this regular expression for reals, I'll replace the dots. Let's say I'll replace the dots with dot plus. Dot plus says match any character 1 or more times. And then I'll replace the dot with a more specific wildcard character. I can do \w for word characters. Here I have the year, so I'm going to do a \d for the year for numbers. I have another number here. I have another number here. Another number here. And I will still match the same thing, but I will get less false matches because I'm using a more specific I'm using a more specific wildcard character. Okay, are there any questions about this? Yeah, Jesse?
So sometimes you use groups and sometimes you use group. What's the difference?
Yeah, so sometimes I use groups and sometimes I just use group. So the singular group says give me the entire match as one long string. So this will give me back like the entire substring of my original string that matches the regular expression. .groups works only if you have parts of a regular expression within parentheses, and that will return to you a tuple containing all the groups within that regular expression. So .group parentheses gives me the whole string. .groups will give me a tuple with all the subcomponents of the original string. Okay, good question. All right. What do I have here? Okay, so this is the better way of matching a pattern. The even better way of matching a pattern is to use Python's like built-in datetime parsing functionality. So I can, from datetime, import datetime. And using the datetime, I can use what's called a time format string. So I can say like the day comes first, and then the month, and then the year, and then the hour, and then the minute, and then the second. This is not a regular expression. It's like a special sub-language as well that Python uses called a format string. And if you want to know how this format string works, you can go in the Python documentation, and they'll describe all the subcomponents of this format string. But in general, if you're working with timestamps, the better thing to do is try to use one of the format string things to match it into a datetime object, because you can do some pretty sensible things with datetimes, like subtract 2 datetimes to get the period of time in between those 2 endpoints. Okay. I do show you this anyway because using regular expressions lets you match other sorts of things besides datetimes. So I can write a pattern to extract out this IP address here. I can write a pattern to extract out this URL here. I can write a pattern to extract out this other URL here. So regular expressions are very flexible because they can match any pattern or most patterns within a string, whereas this particular timestamp can only match datetimes. All right. So bring this back. Okay, so I showed you a bad way of matching a string, which is using the split and like using all the brackets and all of that stuff. I showed you a better way of matching the pattern, which is using a regular expression. And the best way of matching a datetime is to use the datetime module or the built-in datetime functionality within Pandas. All right. One important thing to know about a regular expression is that it's what's called a context-free language, or it's actually like a mini programming language within Python. And regular expressions are implemented by almost every major programming language. So whether they use C or Java or Ruby or Python, all those languages have a regular expression parser that you can use, that you can roughly use the same sorts of regular expression patterns to match strings. It's good for matching patterns, but isn't so good at matching like structures within patterns. So for example, if you're looking for a balanced parentheses, regular expressions are not super great for that. It's good for matching. Specific sorts of simple patterns. Okay. To read a regular expression, you look at the component of the expression, and you look at them, and then you look for the literals that come within the expression as well. So in this particular example, the bracket 0 through 9 here says allow any character between 0 and 9, and have 3 of them. And then followed by a literal dash, and then 2 more digits, and then 4 more digits. So this would match this sort of input, like the social security number. And I have here a table that describes like the 4 basic operations for regular expressions. At the very top, we have the literal regular expression, which just matches the string itself. In the second row, I have the OR operation, which allows me to match one string or another string. I have here the star operator, which allows me to match 0 or more of the preceding character. And you saw me use the plus operator just now, which says match 1 or more. Okay, so the star matches 0 or more, the plus matches 1 or more. Writing a parentheses allows me to use groups within a regular expression, but also allows me to apply operators to components of a regular expression. So in the example I have here on the bottom, I have here parentheses AB, close parentheses star, and that will allow for the repeated AB pattern, but not repeated A's. Okay. I have some more operators. I have here the dot. I have here the character class. So the character class uses brackets. I have here the plus operator, the question mark operator, the curly braces, which repeat a pattern a certain number of times, or repeat a pattern between a certain number of times. Okay, so all this stuff I'm not going to go over in super fine-grained detail because you can look at this table And the best way to learn is to practice using these expressions anyway. So I'm going to have you practice now. On regex101.com, you can type in a regular expression, and it will highlight to you the matched part of the substring. And so what I'd like us to do now is open up this regex 101 here. And you can see here that I have here the substring, the regular expression that I had on my previous slide. Again, if I change this to a dot, it will still match, right? Because the dot is the most general wildcard character. Okay, like so. Let's see here. And I have here a puzzle for you. So I'd like you to go to use regex 101 and write a regular expression that will match moon, moon, or moon. So it should match any positive, even number of zeros. Go ahead and try it out. So go to regex101.com. See if you can write a regular expression that will match the moons I have there, but not mon. Okay, so don't match an odd number of O's, match a positive, even number of O's. All right, I'm going to cut you off here in the interest of time. If that was hard, it was supposed to be. I'm trying to make you squirm a little bit here so you can hopefully remember some of the stuff for later. All right, let me click on that. Okay, so I'm going to cut out the solution for now. I'll write down some strings that I want to match, and some strings I don't want to match. I don't want to match mon. I don't want to match moon with 3 O's. Okay. So again, the easiest thing to do is to take a string and just paste it into my regular expression. That will let me match that particular string, but won't let me match the others. So I can try something like, maybe I can try MO with a plus. MO with a plus matches moon, and it should also match, let me see here. It should also match the others, but it's not. I think there's a setting here I can do, but let me move these into one line here. Let's do global. Okay, so this will show me all the matches. And so writing MO with a plus will match the first 3 strings, but it will also match the last 2 strings, which I do not want. I want an even number of O's. Okay, so the way to have an even number of O's is to say, I don't want a single O repeated 1 or more times. I want 2 O's repeated 1 or more times. And so by putting 2 O's within parentheses, let me zoom in here. Oops. by putting two O's within parentheses and then matching that group multiple times, I only match an even number of O's. Okay. A little tricky. Let's try another puzzle. All right, so try to write a regular expression that will match moon with U's or moon with O's, but not M-O-U-N. So it should be either all U's or all O's, but you should not match a combination of U or O, and they should have a positive even number of U's and O's. Try that out now on the Regex 101 website. All right, let's take a look. So, wrong website. Okay, so I want to match moon, moon, and moon. I also want to match the same strings with U's instead of O's. Let me delete this guy here. I want to match moon with 4 U's. Also want to match with 6 U's. But I don't want to match mon, I don't want to match moon, I don't want to match M-O-U-N or M-O-U-O-U-O-U-N, okay? And so what I can do is write my regular expression here and check to make sure that it matches what I want and not what I don't want. I can start by writing the expression that I had from before, which will match 2 or more O's, but it won't match 2 or more, an even number of U's. So if I want to write the U, if I want to match the U, I can write, let's see here, I can write U plus or O plus, and I have to wrap all of this in parentheses. Okay, so what did I just do here? I said, well, I can match 2 O's, no problem. I can match 2 U's, no problem, by replacing the O's with a U. And so what I want to do is I want to match either 2 U's or 2 O's. And so what I tried to do was use the OR operator to write OO plus. But I noticed that this is not giving me the match that I want because some parts of these strings are not matching. And the reason why they're not matching is because the OR operator comes last. So it gets applied last in the sequence of order of operations for regular expressions. And so what happens here is that it will say, okay, I'm going to look for either M with a bunch of U's or a bunch of O's followed by an N. So you see here, that's the reason why I match OON but not the M at the front. And that's the reason why I match the MUU here, but not the N at the last character. If I want the OR operator to only apply to the U's and O's, I need to make a group. I need to wrap the sub-expression within parentheses so that the OR operator only applies to the U's and the O's as opposed to the entire regular expression as a whole. Okay. Okay, present that. All right. I have here a bunch more slides with some more examples and syntaxes. If you're trying to write a regular expression for emails, this is like the official email regular expression. So in general, if you want to match complicated things with regular expressions, you're better off using something built in. If you're trying to match a pattern, a specific pattern for a particular data set that isn't commonly seen elsewhere, then using a regular expression can be pretty handy and useful to know. Okay, got some more examples, some more tables here. Skip past these guys. Move on to these Python functions. Again, you can look through these yourself, but really the better way to learn about these is to practice using them, which is what we're going to do via lab and discussion, and as well as your homeworks. I will end by talking about, let's see here, the main use case for working with text, which is to extract features for future analysis. So in the inspections data set that we saw for project 1, we saw that restaurants had like a variety of things that they could get marked off for. So some restaurants had like unclean walls, some restaurants had like a wrong food holding temperatures, and some restaurants had vermin infestations. And we might be curious to see like what kinds of violations affect your score the most, right? So what we can do here is we can say, okay, we'll group all the violations related to sanitary issues in one group. We can group all the vermin infestation issues into another group, and we can use those substrings within these violation strings to create features or indicators of what kind of violation it is. So for example, we can take the first violation and mark it as a mark of 1 in the column labeled unclean. I can create these features by writing regular expressions like the following. So here are pretty simple regular expressions. I'm just making use of the OR operator to say cleanliness is represented by being clean or having the sanit characters. So I can match sanitary or sanitization, for example. And if I take a look at the vermin violations in specific, if you do this yourself, you'll notice that if you take the restaurants that had vermin violations and look at their scores distribution, restaurants that have 1 vermin violation still can get a median safety score of 86. This whisker here at the top here says that there are some restaurants, or at least one restaurant, that had a vermin violation but still got a score of 100. All right, so kind of curious. It makes you wonder how they actually do these scores. Unfortunately, we don't actually know the formula. But we can try to derive parts of the formula by looking at the violations and what the scores that resulted from the violations. All right. So, this is fading. We talked about EDA. We talked about text. And we talked about regular expressions. Thanks for coming. I'll see you next week. And have a good July 4th weekend.